Let's begin the final.
طبعا في الفيديو السابق عرفنا أنه هذه المعادلات الطويلة التي عملها المحاضر هي فقط أن يعني يحسب الدبلت أو مثلا يحسب جسيمات من داخل البروتون. هذه الجسيمين هما السيجما والباي، هذه داخل البروتون والنيوترون. ورأينا أن السيجما تمثل الجولدستون بوزونز هي عديمة الكتلة، وأن الباي والنيكلون هي التي لها الكتلة. ورأينا أن خواص السيجما تجريبيا لا تظهر، بالرغم أن النظريات صحيحة لكنها لم تظهر تجريبيا، وإنما ظهرت الباي والنيكلون. وذلك عزينا ذلك لأن الخواص الكهربائية داخل البروتون أو داخل الكتلة عموما، الخواص الكهربائية تكون دائما يعني الطبيعة تستغنى عنها وتتمسك بالخواص المغناطيسية، ولهذا السيجما لم تظهر تجريبيا، بالرغم من أن معادلتها صحيحة ونظريا هي صحيحة ومفترض أن تكون ظاهرة للعيان، وتعبر عن جسيمات الماسلس. رأينا أيضا أن هذه الخاصية بالذات مرصود فيها جوائز، حتى يعني شجعوا الناس أن يفسروا ويقدموا تفسيرات لماذا السيجما لم تظهر، ولماذا الباي ولا هي التي ظهرت. الإجابة طبعا أن الباي هي تعتبر خواص المغناطيسية، والسيجما خواص الكهربائية، والخواص الكهربائية في داخل QCD يستغنى عنها المجال الكهربائي ويتضخم المجال المغناطيسي، يعني يكون على حساب المجال المغناطيسي، يتضخم على حساب المجال الكهربائي، وبالتالي ظهرت الباي جليا لكن لا تظهر إلا السيجما جليا. طيب، هذا الفيديو سنكمل ما بدأناه إن شاء الله في ذلك الفيديو ولنرى.
Chapter in our discussion of spontaneous symmetry breaking is spontaneous symmetry breaking in presence of local gauge invariance. In other words, the Higgs phenomenon and everything that is connected to it. As we just discussed offline, I will not really discuss here the absolute basics, because I know that you know about them from other lectures. So we will not really stress a lot that this is fundamentally important for particle physics and also fundamentally important for superconductors, where there is the Higgs phenomenon. There are no massless Goldstone bosons, but if there is a vacuum expectation value breaking spontaneously such a symmetry, then the gauge bosons associated with the gauge invariance become massive, and the Goldstone bosons become unphysical, and there are maybe some remnant scalar degrees of freedom corresponding to the vacuum expectation value, which can be excited corresponding to the Higgs boson or similar excitation modes in condensed matter physics. So that is all very important and very interesting, but you know that. And here we will discuss a few more detailed aspects which have to do partially with physics and partially with formalisms, and which are quite generic and general, independent of concrete models. And there is in parallel the standard model lecture, where we discuss, of course, the concrete spontaneous symmetry breaking in the electroweak standard model and its physics implications. And here we will do something complementary, and you will see exactly what we will do. So let me first start by saying that there is somehow already a difficulty in defining what we mean by spontaneous symmetry breaking in gauge theories, because what is a gauge transformation? A gauge transformation is a transformation which does not change physics. It only changes the theoretical variables, the theory description of a physical state, but it does not change the physical state itself. Therefore, what can it mean to say spontaneous symmetry breaking, where we would normally mean the vacuum the ground state is not invariant under a transformation. If the transformation doesn't even change the state at all, there is no way that the vacuum cannot be invariant under that transformation. So therefore, spontaneous symmetry breaking in a gauge theory is already kind of a misnomer. So therefore, let's write this down. It does not change physics. And therefore, in some sense, spontaneous symmetry breaking is meaningless. So what does it, however, mean? Very often, and for example, in the standard model and all the other examples that you know, there is both at the same time local gauge invariance and simultaneously global symmetry. Simultaneously with local gauge invariance, and then that global symmetry can first of all change the state, and therefore it can also be spontaneously broken. But in order to quantize a gauge theory, we need a gauge fixing, and the gauge fixing changes the theory, and it also can change the content corresponding to global symmetries. Global symmetries might be broken or might not be broken by the gauge fixing, and therefore the fate of global symmetries and therefore their behavior with respect to spontaneous symmetry breaking can depend on the gauge fixing. So this is a forward, and from now on we will see.
طبعا السبونتانيوس بريكن يعتمد على الجيج فيكسين. هذا أمر مشجع، لأن أنا هذا تواصلت إليه في فيديوهات السابقة، أن الورد ايدنتيتي والإسلافنوف ايدنتيتي كلها غير متطابقة في نظريتي أو في داخل التفاعلات عالية الطاقة، وهذا ما يعطي هذا النوع من الكثر في السيمتري، فهذا أمر مشجع.
Specifically Young-Mills theories, where we know exactly the structure, so it's not just some arbitrary gauge invariance in the sense of first and second class constraints on the Lagrangian, but specifically Young-Mills theories, and there indeed we do have global symmetry and local symmetry at the same time, and we will study what that means. Let us first begin with a discussion of the Goldstone theorem, which becomes invalid. As you probably know, or maybe not, but anyway, historically, when the Higgs phenomenon was discovered by Higgs and others, the big deal was not so much predicting the Higgs boson, but the big deal was to evade Goldstone's theorem. In other words, keep the nice features of spontaneous symmetry breaking, but avoid the existence of massless particles, because in nature there were no massless particles except for the photon. Therefore, one could say there cannot be any spontaneous symmetry breaking unless there is a way to evade the existence of Goldstone bosons. And therefore, this was the big deal of the papers by Higgs and Braud, Angler, and all the others. And so let us see how one evades the Goldstone theorems, because we gave even two proofs of it, and somehow the conditions that go into the proof must become invalid. Local gauge invariance onto our global symmetry. So let us go to the proofs which were done in section 4.4.4 or 4.4.5. So suppose we do a gauge fixing so that we have a proper quantum theory, and even after gauge fixing there is a global symmetry. So it's a particular kind of gauge fixing which breaks local gauge invariance but does not break global gauge invariance. And that is not difficult to achieve. For example, in QED, the ordinary gauge fixing has exactly that property. And therefore, then we can ask this question, what about our field variations in the vacuum? In other words, in this path integral notation, delta phi expectation value at j equals 0, which tells us whether the vacuum is invariant under a symmetry transformation. So if this is true, then that was the starting point for our proofs of the Goldstone theorem. And so let us assume that this is exactly what happens. And going through the proof shows that the proof does not become invalid. The proof just goes through as before, and we show that there is a number n broken, 0 eigenvalues of the 2-point function gamma phi phi at p equals 0. So this is an automatic consequence, and so therefore you might conclude from this that it must mean that there are massless particles in the theory. However, in a gauge theory, after gauge fixing, it can happen that certain types of particles and certain states are unphysical because they belong to a BRST quartet or because they have negative norm and so on. And then those states do not correspond to physical observables, but they are just in our theory in an unphysical sector. So they might be in unphysical sector. And of course, they actually are in an unphysical sector. If you would really be able to prove such a massless particle, then it must be unphysical, because there is no massless particle associated with such a spontaneous symmetry breaking, and in this way you invalidate the proof. There are other ways. You do not have to choose this gauge fixing which leaves the global symmetry. There are also other kinds of gauge fixings. For example, there is unitary gauge. This always exists, and how you can do it is see in the standard model lecture. So there you simply gauge away the Goldstone modes. Can gauge away the Goldstone modes before quantization, and then there is no global gauge invariance anymore, and therefore no spontaneous symmetry breaking and no proof of Goldstone's theorem. So in this case, there is no massless state at all in the theory, not even in the unphysical sector. In unitary gauge, there actually is no unphysical sector. Everything is physical, and there just is no massless state whatsoever in the theory. Then, for example, also, let's put it here, there is arc psi gauges. Also see a standard model lecture. So this gauge fixing has an unphysical sector, but it breaks global gauge invariance explicitly. So therefore also there is no starting point for the proof of Goldstone's theorem, and so there are no massless states in the theory. So for example, in the standard model, the gauge fixing contains this term 1 over 2 psi W for the W boson, d mu W plus minus, let's do it for the Z boson, d mu Z plus mz times the neutral Goldstone boson square. And then you see the Z boson is singled out explicitly and the neutral Goldstone boson is singled out explicitly, but under global SU2 transformations, the neutral Goldstone would have to transform into the charged Goldstone and into the normal Higgs. But in the gauge fixing, the Higgs doesn't appear, only the Goldstone appears, and therefore this SU2 global invariance is explicitly broken by this gauge fixing. And so then you do not have a starting point for Goldstone's theorem, and therefore if you look at this globally, then no matter what you do, you can do many different things, but in all cases the Goldstone theorem does not apply in the sense that there is no physical massless particle that somebody could observe. That was one of the discoveries of Higgs and the other people working on this topic in the 1960s. Let us now study in a little bit formal detail the structure of all the relevant masses in a spontaneously broken Yang-Mills theory. What are the masses of relevance and of interest to us? As you know, most importantly for us today, the vector bosons become massive. And most importantly for the people at the time, the Goldstone bosons become unphysical, even though there might be some massless states inside of the theory. We will look at both. We will look at the masses of the physical gauge bosons, and we will also look at the masses of the unphysical states in our theory, because they correspond to BRST invariants and they must be connected to each other. Everything that is unphysical must be connected by BRST invariants, and we look at both the unphysical and the physical parts of our theory. I use that first of all because I think it is important to understand this general structure, to see the fundamental correctness and validity of this kind of theories. But I also use it a little bit to teach you more how you can actually apply these Slavnov-Taylor identities in practice in order to extract maybe interesting physics information. So let us look at the general structure of the self-energies of all these relevant fields and states, and self-energies of course give information on the masses. So we assume a Yang-Mills theory with scalars. So the fields are A mu, CA, C bar A, BA. This is the list of fields that we need for our BRST formalism to work. So all of this is necessary in order to correctly describe the quantization of gauge bosons. And then we have, in addition, scalars. I will call them small hi, and this is some number of scalar fields. And for simplicity, we assume here that they are all real scalar fields. That is no loss of generality because you can decompose a complex field into two real components. So that is what we assume, and fermions do not matter for this discussion. Then we assume a BRST invariant gauge fixing plus ghost term. And we do not actually care how they look like in detail. Our results will hold in general. And so anyway, what follows from this is a Slavnov-Taylor identity. which I write like we did it recently, gamma star gamma, which is a shorthand notation for this, an integral over space-time coordinate x times d gamma derivative with respect to a source ki times d gamma derivative with respect to a field phi I integrated over the coordinates x. And so the fields phi I here, they run over all the fields of our theory, A, mu, C bar, B, and H. And these are the sources for the BRST transformations S of all the corresponding fields, such that a derivative, precisely this derivative, extracts the BRST transformation of the corresponding field at tree level, and at higher orders it corresponds to some loop-corrected expectation value of such a composite operator. Let us now use the Slavnov-Taylor identity to extract consequences on self-energies, on two-point functions. How can we use that to extract information on concrete two-point functions, such as the gauge boson self-energy, giving us information on the gauge boson mass? Or how can we get information on the Higgs self-energy, giving information d gamma derivative with respect to a field phi I integrated over the coordinates x. And so the fields phi I here, they run over all the fields of our theory, A, mu, C bar, B, and H. And these are the sources for the BRST transformations S of all the corresponding fields, such that a derivative, precisely this derivative, extracts the BRST transformation of the corresponding field at tree level, and at higher orders it corresponds to some loop-corrected expectation value of such a composite operator. Let us now use the Slavnov-Taylor identity to extract consequences on self-energies, on two-point functions. How can we use that to extract information on concrete two-point functions, such as the gauge boson self-energy, giving us information on the gauge boson mass? Or how can we get information on the Higgs self-energy, giving information on the Higgs mass? That is possible by taking further functional derivatives of this identity. 0 is equal to that. If we take a functional derivative, then we get 0 still on the left-hand side. And here we get second derivatives of gamma with respect to something, and the second derivative of gamma corresponds to a self-energy. So then we get relationships between self-energies. Therefore, let's do that. And the general structure is that concrete Slavnov-Taylor identities are obtained by taking functional derivatives with respect to some fields of the Slavnov-Taylor identity, and then setting all the fields to 0. And so let me show you how that works. Example. Let me take 0 is equal to the second derivative with respect to, what do we take? For example, a Fadeev-Popov ghost, CA, and a Nakanishi-Lautrup field, BB. And we do that of this whole Slavnov-Taylor identity, so of this object. What happens if we extract that and set all the fields to 0? So what is going to happen is that we get here an x integral, and then we get second derivatives. For example, we get a term where we get a second derivative, gamma derivative with respect to CA times a source Ki times a derivative, gamma derivative with respect to B, and with respect to the field phi I, where we have a sum over all the possible fields phi I. And if we set all the fields to 0, then this really corresponds to a one-particle irreducible Green function. And now you have to think which one-particle irreducible Green functions can actually be non-zero. Only those ones can be non-zero where things like ghost number is preserved, Lorentz invariance is preserved, and so on. So for example, you cannot have a one-particle irreducible Green function from a Nakanishi-Lautrup field to a ghost field, because that would violate ghost number conservation. Also, you cannot have, what else can you not have? You could not have one Green function from a Nakanishi-Lautrup field to a fermion field, to an electron field, because that would violate Lorentz invariance and so on. You can, however, have a Green function from a ghost to an anti-ghost, and most of these sources here have anti-ghost number, and so therefore you can have a 1pi Green function from a ghost to one of those sources here. That is possible. And then you could also have a Green function from a Nakanishi-Lautrup field to another one, or to a gauge boson, or to a Higgs field, because these are two bosons and there can be a Green function between two bosons. So there are some terms which work and some terms which cannot work. There are also some other possibilities, like for example you could do just the first derivative with respect to a source only, and then applying 3 derivatives onto this sort of thing. Then both additional derivatives act onto the second factor here, and then you have here a 1-point function times a 3-point function, and then again you can ask which 1-point function can be 0. That would be a 1pi diagram with one external source and nothing else. All these sources have non-vanishing ghost number, and there cannot be a 1-point function where just non-vanishing ghost number goes in and nothing goes out. Therefore all these Green functions are 0. Here also you can go through all the possibilities, and all of them violate ghost number. So phi runs through all these possibilities, and then okay, all of them except for one would violate ghost number, but you can see that all possibilities here vanish. So therefore there are not many terms out of all these possible sums distributing the new derivatives and summing over the I, which can actually give a non-zero value. Can somebody from you tell me one term, one concrete field phi I and ki, which gives a non-zero result, or potentially a non-zero result, which is not obviously 0? Can somebody say one example term which could contribute here, which corresponds really to 1pi Green functions which really can exist? Imagining going with phi I, go through all these possibilities and looking, for example, at this term. So if you put here phi to A, then you have here ghost and the source for A and B and A. Can that be non-zero? Can be non-zero. Ghost, then you would have here B ghost. Can that be non-zero? Anti-ghost? Not. B. Then you would have here BB, and here C and the source for B. Could it be non-zero? Principle, maybe yes. Higgs could also be non-zero. Okay, so let us now write down, after thinking a little bit, there are precisely 3 terms which can be non-zero, and all the other terms must automatically be 0 without any calculation. And so we get an identity. 0 is equal to the following. Gamma derivative with respect to Ca, K, how do I want to write it? Hi times gamma BB Hi. So we have set phi to the Higgs field plus gamma Ca Ka mu C times gamma Bb A mu C plus gamma. There is another possibility which looks different from the above. Bb times K C bar C times gamma Ca C bar C. These are precisely the only three possible terms which can be potentially non-zero. And let me write down arguments. We can do it in position space, but we can also Fourier transform and do it in momentum space. And then the x integral simply means momentum conservation. Then we have here a momentum for the ghost incoming p, then minus p, and then here again minus p and p. Then momentum is conserved. Here as well p minus p and p. And here also p minus p, arguments minus p and p. Okay, then let us do another one. That is our Slavnov-Taylor identity 1. A second Slavnov-Taylor identity is obtained by taking the second derivative with respect to a ghost and with respect to a vector field, let's say A nu B. In the same way, you can go through the same procedure and you will get almost the same terms as before, because actually the gauge boson and the B field, they have the same quantum number, so essentially the same green functions can be non-zero. So let's start writing. So gamma Ca Khi times gamma A B nu Hi plus gamma Ca K A mu C gamma A mu B A mu C. But the third term doesn't exist because we already know precisely what is the source doing of C bar. C bar has the simplest BRS transformation. It transforms into B only, and therefore the derivative of B with respect to A would be 0. So this third term has no counterpart here, so we get only a sum of two terms which overall must vanish. Then let's do a third one. We can do a second derivative of the Slavnov-Taylor identity with respect to a ghost and a Higgs field Hj. And you see the logic that I am doing here. I always take one derivative with respect to a ghost and one derivative with respect to one of the bosons. The interesting bosons are the Higgs, the gauge bosons, and the Nakanishi-Lautrup auxiliary field. And so then the structure is always the same because all the bosons have the same quantum numbers. So I get again the same copy of equations where just the A is replaced by the Higgs field or the scalar field. Gamma Ca K Hi gamma Hj Hi, so that would be a Higgs self-energy plus gamma Ca Ka C mu gamma Hj A C mu. Okay, and so you see hopefully now that the Slavnov-Taylor identities that we have produced in this way constrain all the relevant self-energies. So here there is the Higgs self-energy which contains the Higgs masses and also the Goldstone masses, which would be 0 if we wouldn't have local gauge invariance. Somewhere we have the gauge boson self-energy, which gives rise to the gauge boson masses, which would be 0 in the unbroken case and non-zero in the broken case. And then there are lots of other terms, mixing terms, and you know already such mixing terms from the discussion of the arc-psi gauge, because there appear such mixing terms between scalars and vector bosons automatically if you have spontaneous symmetry breaking, and these arc-psi gauges make them vanish through a clever choice of the gauge fixing function. But in general there can be such mixing terms between Higgs and gauge bosons, and also between B field and gauge bosons, and also between B fields and Higgs bosons. All of that can in principle appear. And all of that is constrained by these three identities. And now I want to really evaluate the consequences of the combination of these three identities and derive basically all the consequences that you know from this formalism. And then some of the consequences will hold at all orders, some of the consequences will hold at tree level, and I will tell you why. In general, you should be aware of the following thing. The spontaneous symmetry breaking for global symmetries has rigorous theorems which are non-perturbative, namely the Goldstone theorem. This case here has no such rigorous non-perturbative theorems, and so some statements can be derived in perturbation theory at tree level, and then there are some higher order corrections, and some other relationships can be derived at all orders, but in general the discussion is not as, let's say, generic as in the global case. So, for example, there would not be a non-perturbative theorem that the gauge boson masses must be massive. That is, however, a perturbative statement which can be derived at tree level. And as long as the higher order corrections are small, the statement, of course, survives. But there is no non-perturbative counterpart of that statement. So I want to show you how you can really make sense of this identity and how you can evaluate it in practice. And in order to do it, we should get some analytical understanding of the structure of the self-energies. For example, they have Lorentz structures. The gauge boson self-energy has a transverse part and a longitudinal part, and you imagine that the transverse part is physical, the longitudinal part is unphysical, and so on. This, for example, has one Lorentz index, so if it depends on a momentum p, the result will be proportional to p nu, because there is no other way. This here as well has one Lorentz index, so it will be proportional to p mu. And about some other quantities we know nothing, and some other quantities we know precisely. And so let us evaluate what we know and then simplify the structure of these identities. And maybe actually let me do it on a new blackboard so that this will become a nice table. So the photon or gauge boson self-energy, A mu A nu B, I times that with momentum p comma minus p, that really means this thing, the 1pi green function with momentum p flowing in this direction, and here we have the index AB. And the result of this has two Lorentz indices, and it depends on the momentum. So, and we can factor out an I, and then we can write it by projection operators. On the one hand, minus g mu nu plus p mu p nu over p square times a transverse part AB, which can then only depend on p square, minus p mu p nu divided by p square times a longitudinal part AB, which also can only depend on p square. And then we have done a covariant decomposition of the gauge boson self-energy. And we either in some identities only the longitudinal or only the transverse part will appear, and that is of interest. There is one additional thing to notice. The covariant decomposition has a singularity at p square equals 0, but by construction such 1pi diagrams cannot have a singularity at p square equals 0. Therefore, if we apply regularity at p square equals 0 condition, then we see that this thing can only be regular at p square equals 0 if at p square equals 0 the transverse and longitudinal form factors are the same. So transverse at 0 must be equal to the longitudinal form factor also at 0. Otherwise there would really be a 1 over p square singularity which cannot appear. In perturbation theory anyway. Okay, so next, the Higgs self-energy or scalar self-energy, gamma hi hj, p minus p, that is of course this 1 pi green function from scalar I to scalar j with momentum p flowing in that direction. And here there is nothing else we need to do. This is a scalar and it's simple enough. However, what we can say is what do we know about this at tree level? At tree level we know something about this because this comes of course from the Lagrangian. This is the effective action, so this comes from the Lagrangian, and in the Lagrangian we have a Young-Mills theory. There are kinetic terms for the scalars, and therefore at tree level this must be I times p square times Kronecker delta ij if the scalar fields are normalized in the ordinary way. Then we have this plus a mass term plus higher order corrections. Okay, so we know maybe nothing about the higher orders, we know nothing about the mass term, but we know this about the kinetic term, and that might come in handy. Then next, gamma hi a mu a, p minus p. So this would be such a mixing object where we start with a scalar, the momentum flows in this direction, and we end up with a vector. Here, as I said, the result must depend on a momentum for vector p mu, and we can simply write it as p mu times a form factor which can then only depend on p square. The only question is how do we normalize it? We normalize it with an I times p mu times gamma ha ia of p square. And then we have here a scalar form factor which we can make use of. So this is the most important thing. Then a little bit of additional information. For example, we know the BRST transformation of the gauge bosons. Do you know the BRST transformation of the gauge boson? No? Yes. Normal d mu or covariant d mu? Is there a difference? No, it's the covariant, yeah, plus additional terms finally this is the covariant derivative, but let's just say it like this, and because that is sufficient. So that is sufficient for us now, and the BRST transformation of the anti-ghost is of course the B field, and if you know that, then we know the following, namely I times gamma CB K A mu of p comma minus p. Let's leave some space here and let us evaluate this at tree level. What is this at tree level? At tree level, I take the effective action and I derive with respect to K A mu. The derivative with respect to that source by definition leads to the BRST transformation of A. So that derivative gives exactly this. Then we take another derivative with respect to the ghost, and then we get the prefactor, which is the derivative. But we have passed to momentum space. In momentum space, a derivative becomes minus I times the incoming momentum. Therefore, that thing is exactly minus I times p mu, and then times Kronecker deltas between those things. So at tree level, we get minus and times I gives plus p mu times Kronecker delta AC. Okay. That is precisely the result, and therefore let us in general write the ansatz p mu that must appear times some function which we call capital DAC of p square. And then that is completely general, but we already know at tree level this capital D is Kronecker delta. So this D is invertible at p square equals 0 in the matrix sense. Then next, gamma B B K C bar A. Let's leave out the I here. So derivative with respect to K C bar gives the BRST transformation of that which is B itself. Therefore this also gives delta AB, and that is exact since B has no interactions. So in general there would be higher order corrections for 1pi diagrams between these two, but since B has no interactions there cannot be 1pi diagrams correcting it, and therefore this tree level result is exact. So what else? And maybe most important, gamma CA K HI. What does that mean? Let's give it a name, dAI of p squared. This is a scalar quantity. Let's call it dAI. And what does it mean? The derivative with respect to KHI gives us the BRST transformation, in other words the gauge transformation of a scalar field, and that gives us then really the gauge transformation in the gauge direction A. And if that derivative is non-zero, then it means the gauge transformation of the Higgs in direction A is a constant. What does it mean if the gauge transformation of some scalar field is a constant and not field dependent? It is spontaneous symmetry breaking. That is exactly the thing that in the vacuum this field transforms into a vacuum expectation value. So this would be order parameter for spontaneous breaking of the symmetry. If that is non-zero, then we have spontaneous symmetry breaking. And let's say, just as a reminder, delta phi in the vacuum is non-zero, and here that corresponds precisely to dAI at 0 doesn't vanish. And so as always, the rank of this matrix would count the number of spontaneously broken directions. So we have identified our, let's say, parameter which governs the spontaneous breaking. We have listed all our decompositions for the relevant Green functions, and we have 3 Slavnov-Taylor identities. And for this reason, I think we can now simplify the Slavnov-Taylor identities and write them down in terms of those simpler quantities. Let's do it. And actually, this is a little bit tedious, I have to say. I did it, of course, and we can do it together. But basically, you need to look at all the blackboards and collect all the ingredients. So, for example, for the first identity, we see here this object. That becomes our D, our measure for spontaneous symmetry breaking. So we have here 0 is equal to dAI of p square times that. We have not introduced an abbreviation for this one, BBHI. We have introduced an abbreviation for this one. That was this p mu times capital DAC. We have not introduced an abbreviation for this one, so minus I. So I will write it a little bit from my notes and just tell you basically where it comes from. DAC of p squared times gamma BBAC mu. And then we have this, which we have evaluated exactly, Kronecker delta, and then this is unchanged, so plus gamma CA C bar B. And I took great care that here all the signs are correct and so on. So let's go to the next case. The next Lyapunov-Taylor identity over there, it begins in the same way. It begins with our dA, dAi of p square. By the way, all the arguments otherwise are unchanged, dAi of p square. Then the next is this object for which we have introduced this covariant decomposition. So we get p mu times something. Then finally we have a product of that object which also contains p mu times the gauge boson self-energy. So then in the second line all terms are proportional to p mu. We can cancel the p mu and leave it out of the equation, and then we simply obtain this times gamma HA IB of p square minus dAc of p square times the longitudinal part of the gauge boson self-energy with index BC. And why longitudinal? Because the gauge boson self-energy was multiplied with this p mu coming from the prefactor, and so this kills the transverse part and leaves only the longitudinal part. However, we know that the longitudinal and transverse parts are equal at p square equals 0, and so we can also use that to extract information on the transverse gauge boson self-energy. Okay, so we have that. And the third one is here. It also starts with the same dAi of p square, which corresponds to spontaneous symmetry breaking. Then we have the scalar self-energy matrix. And then we have again the dAc times the p mu, and we also have the other object which is times p mu. So overall we get plus p square explicitly as a prefactor times dAc of p square times this gamma HA JC of p square. And so here you have it. These are our three Lyapunov-Taylor identities in simplified form. They all begin in the same way. You have these D symbols which correspond to either spontaneous symmetry breaking or not. So they are absent if we have unbroken symmetry. They are non-zero if we have broken symmetry. And they multiply certain self-energies, for example the scalar self-energy or some strange mixing self-energies which we are actually not so much interested in. And then it goes on. So this constrains the gauge boson self-energy, this constrains the ghost self-energy, and this constrains the Higgs self-energy. So we can extract information on all the relevant quantities from these identities, and let us do that now step by step.
أنا أريد أن أضيف حاجة هنا. أريد أن أضيف شيء لم أذكره في عندما اشتققنا معادلة الدي فيكتور هذه للجولدستون بوزون. الدي فيكتور هذه تعبر عن المجال، أقصد تعبر عن المجال الكهربائي وتعبر عن المشتقة التي تعتمد على الزمن. طيب، بما أنها تعبر عن المشتقة التي تعتمد على الزمن فإنها لها وضع كالآتي: خارج الكتل هذه المشتقة حية وموجودة، يعني جولدستون بوزون هي موجودة. الدي فيكتور هذا الماثلث هو موجود خارج الكتل، مثل الفضاء الذري مثلا، مثل الهيكز الموجود في مثلا في بداية الكون خارج الكتل. داخل الكتل هي تكون زيرو عن طريق اكسبليكت سيمتري بريكن. لماذا؟ لأن الجاذبية أو داخل الكتل الجاذبية دائما تفضل إلى المجال المغناطيسي. إذن الجولدستون بوزون خارج الكتل تكون حية، أو داخل الكتل تكون ما في. وبالتالي نجعل هذا يدل إلى ماذا؟ خارج الكتل الطبيعة تفضل المجال الكهربائي، وداخل الكتل تفضل المجال المغناطيسي. هذه النظرة، تعال نشوف ماذا يقول هذه النظرة وكيف تمثل ميكانيكا الكم بطريقتها الخاصة هذا الموضوع.
Step by step. Okay, so let us first study the unbroken symmetries. So the gauge group might not be completely broken, such as in the standard model we have a remaining QED gauge invariance, which is unbroken by the vacuum. And so let us assume here that there is a generator A with DAI equal 0, then this symmetry is unbroken, and that might correspond to the photon in the standard model, for example. And from that condition, we will now derive some consequences. So in those three identities, the first term is always 0 and only the other terms remain. So what can we learn from identity 1 at momentum equal to 0? So from identity 1 at momentum completely broken, such as in the standard model we have a remaining QED gauge invariance, which is unbroken by the vacuum. And so let us assume here that there is a generator A with DAI equal 0, then this symmetry is unbroken, and that might correspond to the photon in the standard model, for example. And from that condition, we will now derive some consequences. So in those three identities, the first term is always 0 and only the other terms remain. So what can we learn from identity 1 at momentum equal to 0? So from identity 1 at momentum equals 0, we learn the first term is completely 0 because the D is 0, P is 0, therefore that is also 0, and then that must be 0. That is the gauge boson self-energy. So we get 0 is equal to gamma Ca C bar B at momentum equals 0. And that is true for all B, because A was fixed, but B was just an arbitrary index. What does it mean? If you have a matrix where for this index and for all B, that matrix element is 0, it means the matrix has a 0 determinant or a 0 eigenvector. And therefore, at momentum equals 0, the determinant of this matrix vanishes. And what is the inverse of that thing? It doesn't exist, but it would be the propagator. So it means the propagator of the ghosts has a pole at p square equals 0. That means there is a massless ghost. And which ghost is massless? This one with index A. So Ca is a massless ghost. So we have proven, and this is an all-order proof, that for an unbroken symmetry, the corresponding Faddeev-Popov ghost is massless. Nice, even though not yet physical, because the ghost is not physical, but anyway, we have derived it. Let us look at the second identity at momentum equals 0. The second identity, the first term is 0 because of D, not spontaneously broken. Therefore, the second term must be 0. This contains the DAC, capital DAC, which is a matrix in color space, times the matrix of longitudinal gauge bosons. Let's write it down first. 0 is equal to DAC at p square equals 0 times gamma longitudinal BC at p square equals 0. So we have established that at p square equals 0, it's not written anymore, the longitudinal and transverse gauge bosons are equal. Therefore, this also applies for the transverse gamma. And this is a matrix, an all-order matrix, but at tree level it is Kronecker delta. Therefore, at least in perturbation theory, it will always be an invertible matrix. Non-perturbatively, we might not know, but in perturbation theory, this is invertible. Because at tree level it's Kronecker delta. And so therefore, if we have an invertible matrix times another matrix gives 0, then that matrix, of course, also has a 0 eigenvalue. And so we have a massless vector boson, and not only longitudinal, but also transverse. So a physical massless gauge boson. So we have a 0 eigenvalue of gamma transverse AB at 0, and therefore a massless physical transverse vector boson. And here you see, for example, at all orders, you don't know actually which index corresponds to the massless gauge boson, because that matrix here might be non-trivial. It doesn't have to be the unit matrix at all orders. And so that corresponds to this mixing between the photon and the Z boson, where at all orders you have to renormalize or redefine the mixing between the two such that the photon field operator in the theory really corresponds to the massless gauge boson. In general, you have just some linear combination between fields which correspond to the appropriate particle. But what is definitely established is the massless physical particle state with spin 1 and mass equals 0. And that is a very important physical consequence coming from the unbroken symmetry. And now let us do in a similar way the discussion of the broken symmetry. So let us now assume that the rank of this matrix DAI at 0 is some number in broken generators. And let us, for simplicity, redefine the fields to basically diagonalize that matrix such that DAI at 0 is non-zero for A equal 1 up to that number in broken, and 0 for A bigger than that number. So we have really sorted the generators according to broken and unbroken symmetries, and that is not a loss of generality. It just means that we take some suitable linear combinations. That might not always be practical in a concrete calculation, but for the theory discussion we can definitely do that. And then, of course, now consider the broken case, A being one of the broken generators. Then let me actually begin by writing down some ideas that we have and that you already know, of course. What are the ideas? We expect that for the broken generators the following things happen. First of all, the gauge bosons become massive. So we get physical transverse massive vector bosons.
طبعا تصبح ماسيف في حالة انه يتم كسر التناظر في وجود أقصد هي تصبح ماسف في حالة موجود كسر التناظر. هذا الكسر التناظر رأيناه في الكيو سي دي، حيث أن الكيو سي دي تخبرنا الكسر في التناظر أن الكتل هي التي تعمل على إعادة التناظر. بالتالي نحصل أنه هذا الكسر في التناظر يكون مطبوع داخل الكتل، لكن خارج الكتل لا يوجد، وداخل الكتل يوجد في أنه الكتل تفضل المجال المغناطيسي، وخارج الكتل يفضل المجال الكهربائي. لماذا خارج الكتل أنا قلت لا يوجد وتاني قلت يفضل المجال الكهربائي؟ لأنه قريبا من سطح الكتل يوجد كسر في التناظر. الكتلة لا يمكن تستعيد الكسر في التناظر هذا بسرعة البرق أو مثلا جسر غازات، لا، شغل الأمر متدرج، فيوجد كسر في التناظر على سطح الكتل ويفضل المجال الكهربائي. مثل الذرة نجد أن في خارج الذرة ترتبط الإلكترونات مع بعضها على بعض ويوجد كسر في التناظر خارج النواة، وهذا الكسر في التناظر خارج النواة يفضل المجال الكهربائي. وبالتالي نجد أن الإلكترونات هي تحاول أن تعادل حركة الإلكترونات، تحاول أن تعادل هذا الكسر في التناظر، مما يجعل الذرة متعادلة. وكلما زادت النواة كتلة أو شحنة كلما زاد عدد الإلكترونات، لأنه الكسر في التناظر خارج الذرة يجب أن تكون متعادلة، وهذا ما يجعل الذرة مستقرة، بحيث أن الذرة لا تمثل قوة على الفضاء الخارجي، بحيث أنها تجلب مزيد من الكتل، تجلب مزيد من الإلكترونات، وبالتالي يفعل الفضاء ثنائي الأبعاد آليات الدفاع النفسي، وهذا يكون في صراع مع بعض. لا، يحصل توازن. هذا التوازن تجعل الفضاء خارج الذرة هو فضاء قليل جدا مكسور، قليل جدا. هذا الكسر في الفضاء ما يسبب الروابط التساهمية. إذا الروابط التساهمية تنشأ من هذا الكسر في الفضاء الخارج بعد الذرة. أما الأيون فالأيون يعبر عن كسر كبير في الفضاء ثنائي الأبعاد، التناظر، كسر كبير في التناظر، لأنه هي أصلا الإلكترون الأخير الذي المفترض أن يوضع بحيث أن يجعل الذرة قليلة جدا، تعبر عن فضاء مكسور خارجها قليل جدا. هذا الإلكترون تم نزعه، بالتالي تفعل أو مثلا نزع هذا الإلكترون فيجعل هناك انكشاف لمزيد من التناظرات المكسورة على حدود وجود هذا الإلكترون فقط الذي تم نزعه. بذلك تنشأ روابط أيونية قوية. الروابط التساهمية تنشأ لأنه هناك قليل جدا من كسر التناظر، قليل جدا من كسر التناظر، بالتالي تنشأ روابط تساهمية، خصوصا وين؟ خصوصا في الهالوجينات، لأنه تعبر عن كسر قوي الهالوجينات تعبر عن كسر قوي للتناظر. الغازات. أما العناصر النبية لا، العناصر النبية الإلكترونات وظفت نفسها بأنه تمحي ذلك الكسر، إلا في حالة أنه نعطيها طاقة حرارية أو نسحب منها أي إلكترون. أيضا المعادن، الإلكترون الأخير الموجود في المعادن مثل الصوديوم والكالسيوم، الإلكترون الأخير أيضا استطاع أن يعادل هذه الذرة، وبالتالي أخفى هذا التناظر ما عدا في تكوين السبائك. طبعا تكوين السبائك تحتاج لحرارة، وهذا ما يجعل الإلكترون يرتفع لمدار أعلى ويظهر ينكشف هذا الكسر، وبالتالي يحصل روابط يسمى بمعدنية، روابط معدنية، بحيث أنه تكون بلورة ويكون فيها هذه الحزم، حزم التكافؤ، حزم القاب، وحزم التوصيل وما إلى ذلك. بعد ذلك نجد أن الروابط الأيونية والروابط التساهمية والروابط فاندرفاس، هذه الأشياء مرتبطة بأشياء أخرى. المهم ما أريد أن أقوله هنا أن الذرة تحاول أن تعادل هذا الكسر في التناظر ما تبقى، لأن النواة أخذت جزء كبير من الكسر من التناظر الذي سببه الفضاء ثنائي الأبعاد غير متناظر. ثم بعد ذلك جاء البيئة الداخلية للذرة تأخذ جزء آخر من الكسر في التناظر، وبالتالي ترتبط الإلكترونات حول الذرة بناء على هذا الكسر في التناظر المتبقي. الإلكترونات طبعا برضو في داخلها تأخذ كسر من التناظر لكن خاص بها. بعد ذلك بعد ارتباط الإلكترونات بالذرة وبعد النواة أخذت كسر في التناظر والذرة أخذت وارتباطات الإلكترونات في الذرة كلها تعتبر في المجال الكهربائي، لأنه نحن نتكلم عن فضاء، لا نتكلم عن داخل الكتل، لا نتكلم عن جرافيتي عالي، بالرغم من أنه مجال المغناطيسي الكهرومغناطيسي لديه جرافيتي أيضا، وهذا من سبب القوة يعني كسر في الضعيف. بعد ذلك الذرة لديها كسر ضعيف في التناظر، بعد هذا بعد الإلكترونات وبعد هذه الذرة لديها كسر ضعيف في التناظر، هي ما تسبب به الروابط التساهمية والروابط الأيونية والتفاعلات الكيميائية طبعا. لهذا نجد أغلب التفاعلات الكيميائية إما طاردة الحرارة أو ماصل الحرارة هكذا. السبب أنها تجعلها لأنه هناك إجهاد قوي، هناك إجهاد قوي في هذه الإلكترونات في حول النواة، بالتالي إذا كان طارد الحرارة هذا الإجهاد قوي جدا، إذا كان ماصل الحرارة هذا يعني أن الذرة أكثر تعادلا وأكثر استقرارا، والتناظر كسر التناظر خارجها ضعيف لدرجة بعيدة، لدرجة أن أنت محتاج تديها حرارة حتى تعمل هذا التفاعل الذي يكشف هذا التناظر، وبالتالي التفاعل يغطي هذا التناظر. هذا بالنسبة لخارج الذرة، وهو مجال الكهربائي ينظمه المجال الكهربائي تماما، لأنه نحن نتكلم عن فضاء. داخل الذرة داخل النواة داخل الكتل يفضل ذلك أن يفعل ذلك ما يفعله المجال الكهربائي يفعله المجال المغناطيسي. إذا الآن نحن هنا تناظر مكسور صحيح، وأن الدي اي اللي هو البوستون بوزون تأخذ كتل موجودة في المجال الكهربائي، أو المجال الكهربائي هو من يعبر عن كسر التناظر، أقصد في نظريتي هكذا. ثم بعد ذلك هذه البوزون موجودة، والآن نحن نعبر عن فضاء خارج الكتل. طيب ماذا الذي يحدث؟ لنرى ونفسر بعد ذلك الأمر.
Second, the massless Goldstone bosons become unphysical. So first of all, they exist, and third, they become unphysical. Okay, here I have a different order. So we get also a mixing, as you know from the arc-psi gauge discussion, mixing between the Goldstones and the gauge fields. And because of that, it is actually not enough to say that if you have a massless Goldstone self-energy, that corresponds to a pole in the propagator because of the mixing. And so anyway, let me know, right? The unphysical poles in the Goldstone and longitudinal gauge boson propagators, they must cancel each other out in the calculation of Feynman diagrams, and that must mean that they are located at the same p-square values, so they are at the same positions. They coincide. So these are 4 expectations, and let us prove them all in the remaining time. My question is whether we still need, probably we only need the right hand side of that blackboard. Okay, which identity should we look at first? Let us look at the third identity. Maybe here. Slavnov-Taylor identity 3. What do we see? If we have a broken generator, then DAI is non-zero by definition. It multiplies the scalar self-energies, and here we have an additional term, and the sum of the two gives 0. The additional term starts with p squared times some other regular objects. Therefore, we might not know much about this, but what we know is at p square equals 0, that vanishes. Therefore, we can evaluate the equation at p square equals 0, and then we obtain that this annihilates the scalar self-energy matrix, which corresponds to a massless goldstone, but not really, because the goldstones can mix with B fields and A fields and so on. But anyway, this has the same property as in the case of a global symmetry. It's just not that it means the same thing, but it has the same formal property, namely it is annihilated by the same vector as in the previous case. So the first thing is 0 is equal to dAi at 0 times gamma hj hi at p square equals 0. That's it, as simple as that. And therefore we see that there is a mass, or let's say I would even say would be massless would be Goldstone boson. So we have already established one of our ideas that we had in mind. And why do I call it would be massless? Because this thing is not the inverse of a propagator matrix. It is not, because there is a mixing going on, and so the full propagator is a matrix between all boson fields, and that matrix is a block matrix. It contains this block, but it also contains the mixing block between B and H, between B and B, between B and A, and all these blocks appear, and we should invert the whole block matrix. And the inversion of a block matrix does not correspond to inverting the individual blocks. So that block does not have an inverse, but the entire block matrix might very well have an inverse, and therefore this does not guarantee that there is a massless propagator in our theory, physical or unphysical. We just don't know. We only know this. And this corresponds to this would be massless, would be Goldstone boson. Anyway, the formal property of this object is exactly the same as in the case without local gauge invariance. This is what we can say. Let us go on and extract further consequences from identity 3. Namely, if we write it down once again, so 0 is equal to dAi. How can we say? Times gamma hj hi plus p square dac gamma ha jb. Now at arbitrary momenta, then we already saw that the mass term cannot contribute here. Because that is what we have just established. So in this product, the mass term drops out. Therefore, only the kinetic term can contribute. And we have already mentioned that at least at tree level, we know what the kinetic term is. So therefore, this is equal to p square times Kronecker delta ij plus higher orders. Okay? And so at least we know something at tree level. And at tree level, this was also a Kronecker delta AC plus higher orders. And therefore we can at least establish a tree-level relationship, namely the p square would then cancel, and we get that dA times Kronecker delta is simply that gamma HA. So we get an information on this maybe unimportant looking object. So we get here 0 is equal to dAi plus gamma HA IA at p square equals 0 at tree level. And okay, that tells us that this object is the negative of this dAi, which is interesting because that was the parameter measuring the spontaneous symmetry breaking. Then we can go into the Slavnov-Taylor identity 2 here and plug in our knowledge. We have just learned something about this object. This object is minus DAI. And actually, so therefore you get here DAI times itself, only with a different index AB, minus that thing here. Therefore, we obtain 0 is equal to minus DAI dBi minus gamma longitudinal BC at P equals 0, also at tree level, where I also used that the DAC at tree level is a Kronecker delta. And what do you now see? You see exactly the mass matrix for the gauge bosons at tree level as we discussed them in the standard model lecture. That is exactly the structure of the gauge boson mass matrix. And again, this is equal to the transverse mass matrix, and so therefore we get a tree-level mass matrix M square AB is equal to DAI dBi summed over I for the transverse gauge bosons. And so since for our let's say considered generators A and B, these are non-zero, so we get here a matrix with non-zero eigenvalues, and so we really have massive gauge bosons at tree level. So we have massive physical gauge bosons. And so here you see as an example that we cannot establish an all-order expression for the masses, but at tree level they are non-zero, and so at higher orders there will be corrections, but in perturbation theory there is no way that a correction can drive the mass from non-zero to a zero value. But here there is no non-perturbative or let's say not even an all-order perturbative expression for the mass beyond the Slavnov-Taylor identity. I mean, that is an expression, but it's not a direct evaluation of the mass. But at tree level we can do it. So that is nice.
إذا من هنا من هذه المعادلة عرفنا أن الماس قادم من ماذا حسب نظرية علي يوسف، اللي هو دي فيكتور مضروبة في دي فيكتور، دي فيكتور اي مضروبة في دي فيكتور بي اي، هي قادمة من المجال الكهربائي. قادمة من المجال الكهربائي. هذا من المجال الكهربائي الذي يعطي إلى جولستون ماس، لنرى كيف تعطيها الجولستون لبقية الكتل، لأنه بقية الكتل تتعامل بالمجال المغناطيسي. كما ذكرنا أن خارج الكتل مجال كهربائي، داخل الكتل مجال مغناطيسي. الآن جولستون تحصلت على كتلة وهي عبارة عن مجال كهربائي، أو الجزء المعتمد على الزمن وهو مجال الكهربائي. إذا جولستون هي مجال كهربائي وأصبحت ماسفة الآن. طيب تعالوا نواصل.
And let us now do the final step, namely.
طبعا الدليل على ذلك أن الجولستون والA في المعادلة الأولى عبارة عن ماينس الA اللي هو الجاما بالنسبة للA و H المعادلة الأولى، وA عبارة عن فوتون أو عبارة عن بوزون سبين 1. فبالتالي الجولستون هذه مجال كهربائي، والA عبارة عن فوتون مجال كهربائي. بالتالي هذا جميل، لأنه الفوتون عبارة عن مجال مغناطيسي ومجال كهربائي، لكن لا ضير أن يكون مجال كهربائيا صرفا، لأنه يمكن مثل الطاقة الحركية، الطاقة الكلية يساوي الطاقة الحركية زائد طاقة الوضع، ممكن طاقة الوضع تنقص وطاقة الحركة تزيد. أيضا الطاقة الكلية للفوتون عبارة عن مجال مغناطيسي زائد مجال كهربائي، وبالتالي يمكن المجال الكهربائي يزيد ومجال المغناطيسي ينقص، وممكن العكس. طيب تعالوا نواصل.
Discuss the unphysical sector So these are physical consequences, and let us now consider the unphysical sector, where again these would-be massless, would-be Goldstone bosons appear, and where we consider that mixing that I alluded to. And then we discuss the cancellation of the unphysical poles of unphysical propagators between ghosts and unphysical bosons. Can I delete already this, or do you need this? Maybe we can also delete that one here. Let us look at the unphysical sector. And first consider the bosons. The following bosons exist: scalars, longitudinal vector bosons, and auxiliary fields B. And they can all mix with each other. And among the scalars, some of them are physical, some of them are unphysical, and we have no way at this point to determine which is which. But anyway, in principle, all scalars can mix with the other bosons. So therefore, let us write down a kind of self-energy matrix or a two-point function matrix for the bosons, gamma boson, which is the following 3x3 block matrix. It starts here with a Higgs or scalars, gamma hi hj, and then let me show you the structure first. A mu A nu B, and then here in the final diagonal we have B A prime, B B prime, and so it is a block matrix between all the possibilities of mixing between those particles. So here in that entry we have Higgs I mixing with everything, so Hi mixing with A B nu, and then Higgs I mixing with B B prime. Then here we have A mu A mixing with everything, so here first mixing with Hj, then with A, and then with B. Okay, so and then in the third column we start with B A prime and mix it with everything, so first with Hj, then B A prime with A nu B, and then B with B. And so here we have this 3x3.
قبل أن نتقدم في هذا، هذا ما توصلت، هذا ما ذكرته قبل قليل، أن الهيجز اللي هو الرو الأول والكولوم الأول يعبران عن الهيجز المجال الكهربائي، والتي أخذت طاقة وأصبحت مازف قبل قليل، وتعتبر عن صيغة المجال الكهربائي بالنسبة لنظريتي. أما الجزء الداخلي هذا اللي هو من جميع الروس والكولومز ما عدا أول رو وأول كولوم تعتبر عن مجال مغناطيسي، تعبر عن المجال المغناطيسي في هذه الماتريكس. وبالتالي نجد أن المجال السيمتري بين المجال الكهربائي والمجال المغناطيسي ينكسر، بحيث أن خارج الكتل تمثل المجال الكهربائي، داخل الكتل تمثل المجال المغناطيسي.
The block matrix, and that is the bosonic block matrix, and the inverse of that would be the full matrix of propagators between all those fields. I mean, we have in general established that gamma 2 point to the -1 corresponds to the propagators, and so here we have many propagators, and usually you might be used to the fact where everything is diagonal, and then you have just one gamma for one field and one particle. Its inverse is the propagator, but it works in a matrix sense, and here not only in a matrix sense for the scalar matrix, which would be sufficient in the global symmetry case. That is what I said before, but we have to invert the entire block matrix, and the fact that this has a zero eigenvalue tells you nothing about the fact whether this whole thing has a zero eigenvalue or not. That is what we need. And let me simply say the following. So if the determinant of this bosonic matrix at some P star value is 0, then it means that the propagators have some pole at this very momentum. P star square is a pole in the propagator matrix. Between these bosons. Okay. And I mean, this is completely general. This would even be true if there were no mixing. So if all the off-diagonal elements are non-zero, then the general statement still remains true. But in our case, actually, the off-diagonal elements must be non-zero, as, for example, the Slavnov-Taylor identity tells us. So this is the unphysical boson sector. And then there is an unphysical ghost sector. And here we simply start by assuming that we have a mass of a ghost. So let P star square equal some ghost mass square. We assume it to be non-zero, be 0 of the determinant of the ghost mass matrix or ghost self-energy matrix at P star. Okay. So the determinant of that vanishes, so the ghost propagator has a pole at this value of P square. Then what does it mean? It means literally that the matrix here of the ghosts have an eigenvector with eigenvalue 0, so that means there exists some vector, let's call it xd, which is non-zero, such that xd multiplied with gamma cd c bar d at this particular value p star vanishes. That is what it means. Determinant vanishes, therefore there exists such an eigenvector. And the eigenvector is, of course, not completely 0. Okay? Not. Questions? Determinant, eigenvector. Somehow I see in your eyes that you are not convinced. Are you convinced? Oh, okay. If we have this eigenvector, we now start with, we start with a physical statement that we have a ghost mass, m ghost square, that gives us this eigenvector, and now we construct something. We construct the following vector, namely, let's call it y equal xd, xd contracted with the following gamma cd k hj gamma cd k ab nu 0. We construct that. So we multiply it with some appropriate 2-point functions. And we ask, is this vector y? So it's a vector in the space of fields, in the space of exactly these bosonic fields. It's a vector which has components hj, a, b, nu, and then that would correspond to components for b. So this is a vector that has exactly a structure such that you can multiply that matrix with the vector y. That makes sense. It has exactly the same block structure. Question, is this vector 0 or not? Do we know this? X is non-zero, but if we multiply with this, do we get something 0 or not? So you have to know whether these gammas here are definitely non-zero or whether they could be zero. For example, the first one means our D, these measures of spontaneous symmetry breaking, so we assume that some of them are non-zero. But maybe the contraction with the X maps them to zero. That is not obviously impossible. How about this one? What is that? What do you know about this? We talked about it earlier. So it was this object which at tree level is simply Kronecker delta times p mu, because that corresponds to the BRS transformation of the ghost, which is just derivative of the ghost, so that is p mu times Kronecker delta. If something is Kronecker delta at tree level, it's automatically an invertible matrix at all orders. Therefore here we have an invertible matrix times xd must give non-zero, because it's invertible and x is non-zero. That is proportional to p, but luckily we have assumed that the ghost mass is non-zero, therefore p is definitely non-zero. So that is non-zero, since this is invertible. Then gamma bosonic times y. What is this? We now take the product of this huge block matrix times that vector. So we multiply this with the first object, that with the second object, and the third with zero. What do you obtain by this multiplication? You can look at the upper blackboard and compare. So you get product this matrix times that plus this matrix times that. Where does this appear on the upper blackboard? Unfortunately, we had introduced our abbreviations. Maybe, maybe not copy this, but up to prefactors, this is DAI, and up to prefactors, this was DI, DB. Okay, up to prefactors. And where do you see the combination small d times that plus capital D times that? Where do you see it? The third identity. And the third identity tells us precisely that this times this plus this times the other gives zero. And if you look at the prefactors, then they are exactly correct, such that y times this in the first row gives zero because of Slavnov-Taylor identity number 3. What happens in the second row if you multiply these three with that? So that is multiplied with small d, this is multiplied with capital D. Where does that appear? In the second Slavnov-Taylor identity, and of course the prefactors match such that you get exactly zero. What happens in the third row if you multiply this row with that here? Do you see this also? Probably not difficult to guess where you might see it, but do you actually see it? But there is a catch to it, or a slight difference. What is the subtle difference? So of course it's Slavnov-Taylor identity number 1, where that appears small d times this plus capital D times that. However, the Slavnov-Taylor identity contains something else. What is the something else? It is the ghost self-energy. So that ghost self-energy will now be multiplied in this product with x. And the ghost self-energy times x gives 0. Therefore, it doesn't contribute. And so for this reason, the Slavnov-Taylor identity again tells us that this times that gives 0. And so, long story short, this is what we get. And in words, we can simply memorize the first row follows from Slavnov-Taylor identity 3. Second row follows from Slavnov-Taylor identity 2. And the third row follows from identity 1 plus xd times gamma c bar equal 0. What does this equation tell us now? It tells us that for P equal P star, the boson self-energy matrix is not invertible. Therefore, the boson propagators at this momentum have a pole. That is exactly the statement that the poles coincide between the ghosts and the unphysical bosons. So let's write this conclusion. At P star square equal m ghost square is also a pole of the mixed propagators between the unphysical bosons and so you see, for example, explicitly in the arc psi gauge fixing in the standard model, where the longitudinal vector bosons and the ghosts and the would-be Goldstone bosons all are massive, and the mass is related to the gauge boson mass by the gauge fixing parameter. So, but first let's say that means the unphysical poles can cancel in physical S matrix elements. And so that is a, of course, necessary condition for the independence of the gauge fixing parameter, for example. And so let me just add in arc psi gauge fixing, for example, the longitudinal W plus minus and the Goldstone boson G plus minus and the ghosts C plus minus all have a mass psi W times MW square. And so between the unphysical bosons and so you see, for example, explicitly in the arc psi gauge fixing in the standard model, where the longitudinal vector bosons and the ghosts and the would-be Goldstone bosons all are massive, and the mass is related to the gauge boson mass by the gauge fixing parameter. So, but first let's say that means the unphysical poles can cancel in physical S-matrix elements. And so that is of course necessary condition for the independence of the gauge fixing parameter, for example. And so let me just add in RXI gauge fixing, for example, the longitudinal W plus minus and the Goldstone boson G plus minus and the ghosts C plus minus all have a mass psi W times mW square. So they have a gauge dependent pole, but the pole is the same for all of them. And then the ghost loops come with a minus, and so there is a chance of this cancellation from happening. Very well. We are very good on time, so we can finish now. Let me just finish with a small outlook. So this finishes our treatment of spontaneous symmetry breaking, and in the next lecture we will do another topic. But you can say in principle more to spontaneous symmetry breaking, and I would refer you to the standard model lecture for more details on physical applications, like in the standard model. In particular, two.
طيب قبل أن نستمر تعال نعرف شيء في غاية الذكاء وغاية الحنكة، ويهدم النظرية التي تقول أن في بداية الكون الهيجز بوزون أعطى الكتل هو الذي أعطى الكتل للماسلس بوزونز اللي هو الدبليو وال هذه الماسلس دبليو زي و A دبليو ماينس موجب والجوستون أيضا والجوست. طيب كيف نكذب هذه في بداية الكون؟ ذكرنا أن خارج الكتل المجال الكهربائي هو السائد، وهذا صحيح في متابعين المعادلة واشتقاقات المعادلة، وهذا صحيح. داخل الكتل المجال المغناطيسي. ربما يقول القارئ أو المشاهد هذا جميل، الآن هذه المعادلة تخبرنا أن المجال المغناطيسي زاد على حساب المجال الكهربائي، هذا جميل، وهذا ينطبق مع الطاقة الكلية طاقة الحركة وطاقة الوضع، بحيث أن السقوط على سطح الأرض يحول من طاقة الوضع إلى طاقة الحركة، وهذا جميل. نظرية علي يوسف صحيحة والنظرية هذه صحيحة، لكن الأمر مختلف كيف؟ تعالوا أوريكم الحنكة والدهاء، وهذه الحنكة تثبت وجود الله. الانتقال من الطاقة الكهربائية إلى الطاقة المغناطيسية، الانتقال من المجال الكهربائي إلى المجال المغناطيسي يتحكم فيه شيء معين، وهو الانتقال من خارج الكتلة إلى داخل الكتلة. ليس مثل السقوط على سطح الأرض. السقوط على سطح الأرض نحن نعلم أن إذا كان هناك جسيم فوق سطح الأرض فإنه هذا الجسيم لديه طاقة كلية ثابتة ولديه طاقة وضع، بحيث أن طاقة الحركة صفرا. بدأ في الحركة طاقة كلية ثابتة، طاقة الحركة زادت، طاقة الوضع نقصت إلى أن يصطدم بسطح الأرض. بالرغم من هذه الآلية أيضا تخبرنا أن هناك سطح الأرض موجود، هو المسبب، هذا هو المسبب في كسر هذا التناظر بين طاقة الحركة وطاقة الوضع. يعني هناك آلية، هناك شيء ما سبب هذا الكسر. نفس الأمر ينطبق في الهيجز. الانتقال من المجال الكهربائي إلى المجال المغناطيسي يجب أن يكون فعل السبب، يكون بمسبب. ينتقل من المجال الكهربائي إلى المجال المغناطيسي من خارج الذرة إلى داخل الذرة، من خارج النواة إلى داخل النواة. يجب أن يكون هناك مسبب، والمسبب هو نحن نتكلم في بداية الكون الآن. بداية الكون قالوا الطاقة صفر، وهيكز بوزون كيف يتحصل على الطاقة. الشيء الثاني كيف يعطي الهيكز بوزون طاقته لهذه الجسيمات لو ما كان هناك مسبب، والمسبب هو الله سبحانه وتعالى. الشيء الثاني الخاطئ كليا. إذا حاولت أن تنتقل من المجال الكهربائي إلى المجال المغناطيسي، أو حاولت تنتقل من الهيكز بوزون إلى W، هذا يجب أن يكون هناك phase transition، أو يكون تحديدا انتقال من فضاء إلى فضاء آخر، اللي هو فضاء خارج الكتل إلى فضاء داخل الكتل، إلى فضاء من فضاء خارج الكتل، إذا حيث أن التناظر غير مكسور وهذه طاقة صفرية، هذا تمام، أنا معك تماما أن فضاء خارج الكتل في بداية الكون إذا فرضنا هناك كتل أو خارج طاقة بلانك التي نفخها الله سبحانه وتعالى في الكون، في ذلك الفضاء طاقة صفرية، جميل، لكن داخل الطاقة هذه أو داخل الكتل الطاقة غير صفرية في تناظر مكسورا وفي قوة أنشئت. إذا أردت أن تنتقل من فضاء لهيكز بوزون فضاء هيكز بوزون حيث تكون الطاقة صفرية، موجود هيكز بوزون، بالرغم أن هيكز بوزون أصلا جاء بطاقة غير صفرية، إذا فرضنا أن تنتقل من هيكز بوزون بطاقة صفرية إلى أنه يعطي الكتل لهذه، يجب أن يحصل انتقال من فضاء إلى فضاء آخر، يعني الفضاء غير متجانس، يجب أن يكون الفضاء غير متجانس. فنظرية علي يوسف تضحت أو تفند تماما النظرية التي تقول أن هيكز بوزون في بداية الكون هو الذي أعطى الطاقة وبالتالي لا نحتاج لوجود خالق. لا، الأمر خاطئ، بنظر هذه النظرة خاطئة تماما، لأن أنت بتحتاج لفيس ترانسيشن، والفيس ترانسيشن يحتاج لفضاءين، فضاء فيه طاقة وفضاء خالي من الطاقة. من أين جاء الفضاء فيه طاقة؟ نحن نتكلم عن بداية الكون. من أين جاء الفضاء فيه طاقة؟ لولا أنه كان هناك مسبب، ربنا سبحانه وتعالى هو المسبب، هو جعل ذلك وجعل ميكانيكية هيكز تعمل. إذا كون أن نقول أن هيكز بوزون نشأ عن طريق طاقة صفرية وأعطى طاقته للجسيمات التي نراها الآن برضو في عن طريق الطاقة الصفرية، هذا خاطئ تماما.
Two things are noteworthy in this more formal context. One is what we discussed in the standard model already, namely the BRST structure of the theory with spontaneous symmetry breaking is interesting, and we get from the BRST transformation laws information on the physical and unphysical states. And so looking at the structure, we automatically obtain the information that the massive gauge bosons have 3 physical degrees of freedom, the Goldstone bosons and the 4th degree of freedom for the gauge boson, and the ghosts, they form a BRST quartet, and so they are all unphysical, and so the BRST structure matches with our intuition and the knowledge from simple tree-level calculations. And the BRST structure can be evaluated not only at tree level but also at all orders, and then exactly this discussion that we are doing here tells us the all order information that we need to know in order to determine the linearized BRST transformations of all the fields in the full theory at all orders, and then we can determine the physical and unphysical degrees of freedom in the same way, and these consequences here, they are of course all order consequences to establish the physical meaning of the theory. The other remark which I want to make is there is the so-called Goldstone boson equivalence theorem, which is an interesting statement between physical processes, physical cross-sections for longitudinally polarized physical gauge bosons on the one hand, and on the other hand amplitudes with unphysical Goldstone bosons. So they become equal in the high energy limit, and Goldstone bosons, even though they are unphysical, can be calculated more easily because they are scalars, and so that gives a simplification for certain calculations. And the proof of this Goldstone boson equivalence theorem can also be done using similar methods as the ones that we have applied here. So just that you know this as well. Question? It has to do with it, even though it's maybe not exactly the same statement. That sort of statement is what you see in direct explicit tree-level calculations, which we have not done here, but they would be easy to see in the standard model lecture, where you at one point derive those mixing terms, and where you see that from the kinetic terms of the theory, you at some point end up with something like this, where you get a combination gauge boson plus charge times some prefactor times d mu of a Goldstone boson. And so you see that precisely this linear combination is what appears in the Lagrangian, and that shows you on the one hand that the Goldstone bosons can be absorbed into the gauge bosons by some gauge transformation, which leads to unitary gauge, but it also tells you that the Goldstone bosons are immediately unphysical because they only appear in this combination. They do not appear alone and in isolated form. They only appear in this combination together with the gauge field. And since they become unphysical, you can use this sort of appearance to argue in this way that the Goldstone bosons are absorbed by the gauge bosons and give them the additional third physical degree of freedom. And yeah. Okay, let's stop here. There is another interesting lecture that I want to attend, and so I'll see you next time.
إذا كانت كده طبعا نكون انتهينا من السلسلة الثانية والحمد لله. بقيت لنا السلسلة الثالثة وهي الستاندرد موديل، سندخل فيها إن شاء الله إما خلال اليوم إما بكرة بإذن الله تعالى. و يعني أسأل الله أن يكون الستاندرد موديل سهل وبسيط، لأنه عامل لي إشكالية كبيرة جدا، لأنه هناك فجوات كثيرة في نظريتي لم تستطيع تغطيها. طبعا هذه السلسلة قدمت لي كثيرا من المفاهيم الجميلة جدا جدا بخصوص والتي يعني ابتكرت لي موضوع انه التناظر ينكسر بين المجال الكهربائي والمجال المغناطيسي، بحيث المجال الكهربائي يعمل خارج الكتل والمجال المغناطيسي يعمل داخل الكتل. هذا يشترط في ماذا؟ يشترط أن يكون التناظر أصلا مكسور في الفضاء ثنائي الأبعاد، وكسر التناظر في ثنائي الأبعاد يولد قوة. القوة ليست هناك مشكلة، القوة تكون موجودة في الفضاء ثنائي الأبعاد، لكن إذا حصلت أنها جهات كتل، هذه الكتل تكسر التناظر في الطاقة الكهرومغناطيسية، بحيث أنه تجعل خارج هذه الكتل تعمل المجال الكهربائي يسيطر عليها ويسيطر على الفيزياء، يعني خارج الكتل، وداخل الكتل المجال المغناطيسي يسيطر على الفيزياء. أما ناحية الكتل ذاتها وجدت الفضاء ثنائي الأبعاد يجد طريقة لإنقاذها عن طريق الآيس سبين، بحيث أنه يجعل الكتل تفني بعضها البعض من خلال ما يسمى بالكوارك وأنتي كوارك، أو المادة والمضاد للمادة، بطريقة أو بأخرى لا أعلم كيف، لأنه كلها المضاد المادة والأنتي ماتر والأنتي ماتر الاثنان يتجاذبان في جاذبية واحدة. بالتالي هذا الفضاء ثنائي الأبعاد عليه مهمة كبيرة جدا جدا أن يلغي هذه الكتل بطريقة أخرى، لأن الجاذبية تعمل الاثنان عليهما الاثنان بطريقة واحدة. فربما ابتكر هذه ما يسمى بالآيس سبين، بحيث أن الآيس سبين تستخدم ما يسمى بالجيروسكوب. في الجيروسكوب نحن نعلم أن الجيروسكوب في لديه آلية أن يلغي الجاذبية بالمناسبة، وهذا مصنوع منها الطلق النارية والدانات والصواريخ، اللفة المغزلة لهذه الصواريخ وهذه الدانات والطلق تعمل على مبدأ الجيروسكوب، بحيث أنها تلغي قليلا من الجاذبية. وهذا ما يفعله الفضاء ثنائي الأبعاد من أجل محاربة الكتل. في ظل محاربة الفضاء ثنائي الأبعاد للكتل يترك الطاقة الكهرومغناطيسية كما هي، أو يقمعها قليلا أو يتركها بالكلية. بالتالي هذه الطاقة الكهرومغناطيسية تظهر خصائصها داخل الكتل وخارج الكتل بطرق معينة، بحيث أن التناظر يكون مكسورا. وهذا ما يعطينا التشابه الكبير جدا بين الكيو سي دي والاي دبليو والاي ام، يعني الطاقة النووية والطاقة القوى الضعيفة والقوى الكهرومغناطيسية للذرة. كل هذه الثلاثة تتشابه من حيث تفاعلاتها، من حيث المدارات، الفضاء مقسم في مدارات داخليا، ومن حيث أن المجال المغناطيسي أو داخل الذرة داخل الأنوية أن الكيو سي دي تتعامل ببايدن انرجي شبيهة تماما خارج الذرة، وربما يكون مقلوبا أو معكوسا تماما في خارج الذرة أو خارج النواة، حيث هذه الطاقة تمثل طاقة في خارج النواة تمثل طاقة الذرات أو الأنوية عندما تتقارب وتتباعد. منحنى مشهور للطاقة الكلية مقابل نصف القطر، هذا المنحنى مشهور جدا. نجد أن داخل الأنوية الأمر أيضا يكون صحيحا لكن معكوسا تماما. والانعكاس الناتج من ماذا؟ ناتج أن اخترنا محاور مختلفة، حيث أن في الطاقة الذرية نجد أن المحاور هي الطاقة الكلية مقابل نصف القطر. أما في البايدن انرجي في الطاقة النووية هي الطاقة الكلية مقابل عدد النيوكلونات، فهنا الأمر مختلف، بالرغم أن عدد النيوكلونات تتناسب مع نصف القطر، كلما زاد عدد النيوكلونات زاد نصف القطر، وبالتالي هذا يعطينا أمر مقلوب بالنسبة للكيو سي دي والإلكترومagnetic. ربما هذا الانقلاب ناتج من أن الكيو سي دي تعمل بطريقة عكسية، بحيث أن الإلكترومagnetic معروف أنه إذا تقاربت الجسيمات تزيد هذه الطاقة، وإذا تباعدت الجسيمات تصل هذه الطاقة إلى الصفر، طبعا أيضا تزيد وتصل إلى الصفر. في حالة الكيو سي دي نجد أن إذا تقاربت أو الطاقة النووية إذا تقاربت هذه الجسيمات نعم تزيد هذه الطاقة بفعل الفضاء ثنائي الأبعاد يبعدها من بعض البعض. نتكلم عن عدد النيوكلونات ونصف القطر. هنا إذا تقاربت النيوكلونات من بعضها البعض فإن شحنة البروتون تعمل على تباعدها من بعضها البعض، وهذا واضح. أو في حالة أنها بعدت عن بعضها البعض فإن بايدن انرجي تعمل على تجاذبها مرة أخرى بعضها البعض. لكن بما أننا نتحدث عن عدد النيوكلونات فإن حتما زيادة عن عدد النيوكلونات حتما يؤدي إلى تباعد هذه الجسيمات أو يؤدي إلى انشطار الذرة وتباعد الأنوية، لأنه البروتونات تلعب دورا كبيرا في هذا الموضوع. وإذا هناك تشابه كبير جدا بين الكهرومغناطيسية خارج الذرة وخارج النواة والكهرومغناطيسية داخل النواة، بحيث أنه خارج النواة تكون المجال الكهربائي مسيطرا وداخل النواة يكون المجال المغناطيسي هو المسيطرا. وهذا يؤكد مرة أخرى نظريتي. سنختبر هذه الفرضية وفرضيات أخرى قالتها نظريتي في الستاندر موديل، وسنرى كيف تفعل، هل يكون صحيحا أم لا. طيب، السلام عليكم ورحمة الله.